So this topic is the logical kind of development of what we have done before. We have now all the tools and knowledge and skills to model the causal effects of some variables of interest x on the dependent variable y. So far we studied the linear models where the effect on y of a unit change in x is constant. Well, we never allowed this causal effect to change depending on something. In reality, it is not always true. In reality, these causal effects might change depending on different variables. And now the question is, what if this effect, what is this causal effect, changes? And it might depend on one or more of the regressors. In this case, the population function is going to be nonlinear. And today we will discuss how to model, how to deal with these nonlinear functions and how to model them, how to interpret the results. And this is just a development of the previous 3 lectures when we spoke about multiple regression model, because all we need to do is slightly modify those multiple regression models in order to allow these nonlinearities. So here is the illustration of the meaning, why we are bothering with these nonlinear functions. So before, we assumed that when we increase x by some amount, the effect on y is constant, and well, the graphical representation is just a straight line. What if this effect depends on the level of x? For example, for small x's, like the change in x, a small increase in x, corresponds to the large decrease in y. On the other hand, when x is large enough, we are not able to maintain the same effect, and we need large increase in x in order to produce at least some effect on y. So this is a nonlinear effect, and you know from other economic subjects that these nonlinear effects, they kind of present in reality. This is something like diminishing marginal productivity of factors of production, diminishing utility of consumption, and many other things. They may have such form, and we want to have such effects in our models. Another case of nonlinearity is the following. Suppose that we have 2 groups of objects, and we can model these 2 groups, we know, with the binary variable. Either x2 is 0 or x2 is 1. So like the other regressor. And for the group where x2 is 0, we may have flatter line, while for the group where x2 is 1, we can have a steeper line. This is another case of nonlinearity because we have a slope that depends on the value of x2. And this is another case that we will introduce today. So is this clear? What are we looking for?
Кажется, да.
Yes.
Perfect that you started speaking Russian. Okay, so for this lecture we will extend the previous example of test scores, and we will do the following exercise today. So we suggested that economic background of students may affect the performance, and we modeled this economic background previously with 2 variables. One variable was the percentage of students qualifying for subsidized lunch. We used this as a control variable in multiple regression model. And another proxy for economic background was the percentage of students whose families qualify for income assistance. We haven't discussed this in lectures, but you've read the paragraphs in chapter 7 from the book, and authors suggested this another variable to represent the economic background. Today, we will use another variable which is going to represent the economic background of students in the district. This is the average annual per capita income in the school district. So, like average income of families, if you want. And suppose that we want to know how test scores depend on this district income. Here is a scatter plot. What do we see? Whether this effect is linear. Yeah, we see that it is somehow diminishing. For districts with low levels of income, we have a steeper slope, while for the districts with the middle income or even large income, the slope is almost zero. And if we try to fit the straight line, this straight line will not be the perfect fit to this data. Maybe we want to model some nonlinearity in this in the model, and this is the first step. If you want to find out whether the nonlinearity is present in the data, you need to draw the scatter plot. So the scatter plot easily shows you if you need to implement what we are talking about in this lecture, if you need to implement these models. If you see suggested nonlinearity, then you start doing start applying these methods. So yes, it seems that the relationship is not a straight line. And now the question is, what kind of functions from mathematics, all of us know mathematics, so what kind of functions from mathematics can model this relationship better? Any ideas?
Was it something like hyperbola?
Something like what?
Hyperbolic function or
Well,
something.
hyperbolic function is when it's diminishing, so probably hyperbolic function would be better for this.
Okay.
Right? Because hyperbola is 1 over x, for example. This is hyperbola, 1 over x squared. But in this case, what might help us?
Just a second. But I'm totally sure that it is hyperbola.
It's parabola, it's not hyperbola. Might be parabola, right?
No, parabola.
But one part of parabola, I mean, only if it's parabola with the negative coefficient on the squared element, and the parabola fits good. Look, because it goes down here, it slightly goes down, and we probably can even model this maximum, the point of the maximum for the parabola. Well,
I'm totally sure that it is not parabola.
Okay, so you will prove me later, and I will prove you that this is parabola, or probably something else. Yes, well,
I just googled it. I did.
Sorry.
Sorry.
So it's not symmetric parabola, right? I mean, it's only the part of parabola. It doesn't go like it's not reverse U-shaped, of course. It's not the full parabola, but the left part of the parabola, which is a reverse U-shape, is more or less nice. And this is the easiest way to think about this. Well, hyperbola might be also possible, but as I said, hyperbola is useful when you see this reverse effect, like this, when it diminishes, when it doesn't increase. And another possibility for this function is not related to the powers. What's that?
What?
Another function that might fit this data.
Hyperbola. There was a hyperbola, parabola.
You are trying to tell me something about the shapes of curves, but what if you think about the functions like x squared, x cubed, or something else? What these?
X squared x.
It's
Part
polynomial, right? So x squared is polynomial, and another version is a logarithmic function. So the logarithm also looks like this. For the low values, we have the large slope, and for higher values, we have almost zero slope. This is the logarithm. Just another version. As I said, yes, you are right. We are not talking about this, but basically we can also apply hyperbolic functions. We can apply something like square root function, whatever, because square root also looks more or less similar to this. All these things are gonna be based on the same idea. So for this lecture, we will talk about polynomials and logarithmic functions, but as I said, in principle, with these tools, you can model any kind of relationship. If you see that it looks more like hyperbola, like 1 over x, you can do the same. If it looks like square root, you can model this as square root of x, whatever. The ideas and the approaches are totally similar. So, this is an illustration. We fit a straight line, we fit this is the polynomial of order 2, and definitely this, you see that this is some kind of like the left part of the parabola with the maximum somewhere around here. So we can somehow extend it to the right. And obviously this graph fits better than the left one. So now, how can we specify the model for this regression line? Very easy. We just put test score as the dependent variable, and we put first and second order of average income into the model. What does this look like? Like a multiple regression model, where one regressor is average income, and the second regressor is average income squared. No problem with estimation of this model. So, and this is called the quadratic regression model. How to estimate betas for this model? We know that this quadratic regression model is just a particular version of the multiple regression model. One regressor is average income, and the second regressor is average income squared. Nothing is different from the previous material. And we can create this second regressor simply by generating a new variable that equals to the square of average income. So for example, if you want to do this in Python, you can create a new variable. You know how to create new variables, which is going to be average income squared. And then you put these two variables, average income squared, into the regression. You estimate betas, and you have the estimates of the regression curve, because now it's not a straight line anymore, it is a curve, and everything else is the same. So just apply OLS. For this model, when we estimate this model on the data of about the test scores, we have the following estimates. We have, this is an estimate on the average income, and this is the estimate on the average income squared. Are the coefficients significant? statistically significant?
Yes.
You can simply count looking at the coefficient estimate and at the standard error. And if the standard error is less than 2 times smaller than this coefficient, then everything is okay. So here we see that this is 0.04 and this is 0.005, so which means that t-value is around 10. And here t-value is also around 10, so everything is okay. And this is how we can prove that squared specification is better than the linear one, because this coefficient is statistically significant, which means that the coefficient on the squared term is present in the population model, in the population model. So all coefficients are significant, non-zero, and now the question is, so remember that we started this lecture with the idea that we want to model the causal effect, the nonlinear causal effect of a regressor on the dependent variable. So in this case, now we really need to understand what is the interpretation of these coefficients, because the interpretation is not the same as for the multiple regression model. Look, we cannot say that 385 is the decrease in the test score when average income increases by 1. It is measured in $1,000, holding all the other regressors fixed, because we cannot hold this regressor fixed. Obviously, if average income changes, average income squared also changes. Therefore, we need to understand what is the effect of a test score on a unit change in average income. Who can suggest how we can do this, how we can quantify this effect? This is very simple. If you know mathematics, if you remember intermediate microeconomics, it's
so
simple.
Maximize.
No. We want to know the effect.
Derivation.
Derivative, of course. We take derivative of a test score with respect to average income. Here, 385 minus, so 2 multiplied by the coefficient on the squared term times average income. And look what we see. We see that the more the average income is, the less is the effect of an unit change in income on the test score. If average income is low, this change is going to be large. For example, if average income is 10, you put 10 here, multiply by this, it's 385 minus 0.8, right? So the effect is going to be around 3. If average income is 50, you multiply this by 50, it's going to be something like 4. And 385 minus 4 is going to be even negative. So the further increase in average income will decrease the test score. That's simple. Now we have very nice model that allows us to show that incomes are not homogeneous. Districts are not homogeneous. So in this effect, the poorer districts have larger benefits of reduction in the class size compared to the more wealthier districts. Yeah, so the marginal effect is diminishing. When income gets higher, the effect becomes weaker and might become even negative. So, for example, if income changes from 10 to 11,000 USD, so this is very simple. You take 10, you plug it here, you calculate the test score, and then you take 11, plug it here, and calculate the test score and calculate the difference. This is very simple. I guess no need to put this on slides. So the test score changes by 296 on average. Well, this is an effect when district gets wealthier here. And if income changes from 40, sorry, I was explaining you from the class size. Yeah, I was wrong. There is no class size here. There is only income here. Yes, so only when the income increases by some amount, the test score increases. For if a district becomes, if a relatively poor district becomes slightly wealthier, like by 1000 USD on average, the test score because of this increases around to 96. But if the already wealthy district gets wealthier by 1000 here, the test score changes only by 0.42. Yeah, no class size effect here yet, so we will talk about this, but not now. So this is the idea of a polynomial. Any questions here about the interpretation?
No questions.
In general, if we step from this example to the, let's say, to the general model of the polynomial regression, we can allow for any order of for any degree of the polynomial. If r is the highest power of x in the regression, then the polynomial regression model is here. So we simply put first, second, third, etc. till rth order power of x. And when r is 2, this model is just a quadratic regression that we discussed on the previous slide. When r is 3, the model is called the cubic regression model, and all the polynomials of the higher order, those are just polynomial of order 4, of order 5, and so on. What is interesting for us here is to compare this nonlinear model, polynomial, with the linear model and ask ourselves if we have enough evidence to claim that the relationship is indeed nonlinear. Which means that if there is a linear function, these quadratic and higher degree terms, they simply do not enter the population regression function. How we can answer this question? Again, remember the previous material. If you want to compare, or if you want to claim that the model is nonlinear or model is linear, what kind of hypothesis should we test?
That the x quadratic x is significant statistically.
Betas. But
Yes.
which exactly? Which coefficient must be significant or not significant?
Significant or coefficient of quadratic, like the squared.
How about this? For example, the rth power.
Also.
So what kind of hypothesis do we need to test if we want to claim that this model is not linear? Let's look. Linear is this part.
That the beta r is 0, like the null function.
Only beta
or
r.
Null hypothesis.
What about beta 2?
Wait. Everything. Oh, wait. Joint.
Of course.
Hypothesis.
We want to test the joint hypothesis. And the joint hypothesis is that all coefficients of higher order powers are 0. So beta 2, beta 3, up to beta r, they jointly are 0. And the alternative hypothesis is that at least one of these betas is not 0. We don't care which one, but if at least one of them is non-zero, then we reject the null hypothesis and we believe that there is a polynomial and there is a nonlinear relationship. If we fail to reject this null hypothesis, then we believe that the relationship is linear. This is obvious. And we know how to test this hypothesis. We spoke about this last week. We apply F statistic, better to apply the heteroscedasticity robust F statistics, and the number of restrictions is Q equals R minus 1. So R is the degree of polynomial, and minus 1 means that we are not testing that beta 1 is 0, because this is not reasonable. We want to compare nonlinear model with the linear one. In our example, if we estimate, for example, a cubic regression of test scores on district income, we will get the following result. And so all the coefficients individually are significant, even this one. So there is almost 2. And at 5% level of significance, this coefficient is okay, is statistically significant. And we can test the joint null hypothesis that beta 2 and beta 3 are both 0 versus the alternative that one of them is not 0. Again, remember from the previous lecture that we cannot tell whether H null is rejected or not, simply looking at the significance of these two coefficients, because in this case the probability of rejection of H null increases. So therefore we need to apply the heteroscedasticity robust F statistic. We compute this, and there is 3769, and p-value is something like 0.16 then there is something, so it's much less than 1%. So therefore we failed. We can reject H null. The relationship between test score and district income is nonlinear. And now we can also compare the quadratic specification with the cubic one. And how to do this? Easy. We just look at the significance of this single coefficient. If we want to test whether quadratic or cubic polynomial fits better, we simply look at the significance of this cubic term. And we see that the coefficient average income cubed is statistically significant, but only at 5% level. So let me show you that if we compute t statistic for this coefficient, we take 0.3069 over 0.3035, and the t statistic is 197. And you remember that the critical value is 196. So it's very close to being not rejected at 5%. At 1% significance level, we are not able to reject the hypothesis that this coefficient is 0. Therefore, we are kind of unsure which model is better. It might be cubic polynomial, it might be quadratic polynomial, and therefore either one of the other fits the data, but well, it depends on our goals and it depends on our needs. We can also treat this by the r squared, but r squared for the cubic polynomial is going to be always larger than for the quadratic one. It's just that r squared might differ. We will look at them tomorrow on the exercise session, and we will compare the two by the r squared.
Can we leave both of them quadratic and cubic?
We can, yes, but be careful, because we are kind of at the margin of not rejecting H null regarding this single coefficient. So that's why we can probably use both of them. because look, the model itself is not what we want. We are just talking about the nonlinear relationship between average income and the test score, but as the kind of ultimate goal is still the investigation of the test score effect on the of the class size effect on the test score, and we will use this and these regressors and maybe the cubic of average income also as control variables. So this is the ultimate goal of the investigation. So usually in the research you can use quadratic polynomial and also cubic polynomial and look at the change in your estimate of the effect of a class size on test score. If this difference is large, then probably cubic term matters. If this difference is not that large, maybe cubic term does not matter. So this is if we are using this approach for causal effects. Another question is about if you want to use this regression function for predictions. This is another issue, because the larger order of polynomial you use, the better is gonna be fit and the better is gonna be r squared. But usually these higher order polynomial models will produce very bad and very poor predictions. Why? Because, well, when you, for example, look, let's have a look at this data. If we fit, let's say, the third order polynomial here, there is going to be some curve, maybe more or less similar to this one. And of course, if we want to predict what will be the test score for districts with larger income, like 60, 70,000 and so on, we obviously see that it will be declining. But the problem is that we have scarce data on this right side of the distribution. There are only like 1, 2, 3 districts with the income larger than 50. And these districts kind of bend this line downwards. If you drop these districts, what will be the effect? Probably if you drop these districts, the effect is going to be that the line continues to grow at the lower rate. And the ultimate kind of idea of what I'm explaining is that if you use like third, fourth, or fifth power polynomial in order to make predictions, it will perfectly fit your data. It will be kind of very nice and very large r squared. But if you want to make some out of sample predictions, this polynomial will fail with large degree of certainty. Why? Because it is very sensitive to every point in your data. And if the points are not representative, then it's not very nice. So better to use something simple. First, second, at most third order. There is some rule called that all the models must be parsimonious, which means that they must be as simple as possible. Okay, any questions regarding polynomials?
So if we use them as control variables, the same, like, I'm just having issues that they are, we can change one without changing another, and our quadratic coefficient is a control variable.
No. The control variable is average income. But if we know that this control variable has a nonlinear effect on test score, we can include average income in like several in the polynomial form, like average income squared, average income cubed at most.
Oh wait, so
kind of it's still it's one variable. Practically, it's
yeah.
one variable, but this one variable enters the regression in the first power, in the second power, in the third power. Technically, yes, technically we treat average income and average income squared as two different regressors, but logically this is the same variable, right?
Yes, and given this regression, average income is the variable of interest, and average income squared
It
is
depends.
control
It
variable.
depends. If you want, for example, if you look at this model, in this model, average income is a variable of interest. Yes, we want to understand how average income affects the test score, right? But we abstract in this model, at least for now, we abstract from all this discussion about conditional mean independence, about omitted variable bias, and etc. Because the most important message here is to show how these nonlinear models work. But when we come back to all the discussions that was made before about omitted variables, about the conditional mean independence, and so on, definitely we cannot claim that this is the true causal effect that we have found. We need to look at some other determinants of average income, test scores, and all the other things. Well, don't think about these numbers as the estimates of true causal effect. No, because all this discussion is left aside. Now we just need to understand how these nonlinear things work when we include them into the regression. And this is going to be a home assignment. Basically, you will read the part from the book which discusses what happens if we include this polynomial as the control into the regression of class size, of test score on the class size. What happens in this case? Okay.
Okay, and also if we include if we want to include the variable of average income in the regression model, do we include only one that is, for example, quadratic, or we
No.
include both?
First and second power, and probably the third one.
Okay.
Probably, but I mean, as we see, the third power is at the margin of being not rejected.
Okay, I see. Thank you.
Now we move to the second function that is able to model these nonlinearities, and this is the logarithmic regression function. And you will see logarithms in many different applications. Well, for example, I decided not to bother you with this material before, but the last two home assignments that you did, like 3 and 4, when you investigated how wage depends on experience, or like experience, yes, I guess. Oh, education, sorry, education. How wage depends on the education. So wage was measured as logarithm of wage. It's not like the level wage, it's a logarithm of wage. So I decided not to bother you during the home assignment, but now you will understand better what happens there. So first of all, what this logarithm does from the practical side, we switch from levels into percentage changes. So the logarithm approximates the percentage change of the variable. And so many relationships in economics are naturally expressed in terms of percentages. In our case, the question will be a change in district income of 1%, not $1,000, but 1%, is associated with a change in test scores that is approximately constant for different values of income. So this is going to be a question. So probably I needed to formulate this as a question. So this is a question sign, but you see that now we are switching our attention from asking what is the effect of $1,000 change to the question what is the effect of 1% change. And obviously 1% change when the initial level is 10,000 differs from the 1% change when the initial level is 40,000. I hope you understand, right? So if we change 10,000 by 1%, there's going to be 11,000. If we change there is going to be 10.1 thousand, yes, if it's 1%. If we change 40,000 income by 1%, there is going to be 40.4 thousand, right? And definitely, this also is a nonlinear relationship. And moreover, what you need to understand, this is used in many, many applications. This is used in finance. This is used in economics and econometrics. We approximate with the logarithm, we approximate the percentage changes in the variable. So basically, if we take the logarithm of x plus delta x minus the logarithm of x, so this is the difference in logarithms, this is approximately equal to the percentage change in the variable x, so delta x over x. Again, this is not exact equality, but if delta x is small, this is more or less nice to treat this change in logarithm as a percentage change in the variable. And this is needed to correctly interpret the meaning of regression coefficients, because the meaning of regression coefficients now changes. Let's see how this works when we specify the logarithmic regression function. So there are three cases of logarithms in regressions. So the first case is called linear log model, and the linear log model looks like this. So y is level and x is taken as the logarithm of x. And the interpretation of beta 1 is the following. So a 1% change in x, why it's 1%? Because it's under logarithm. 1% change in x is associated with the change in y of 0.01 times beta 1. So where this 0.01 comes, because we are talking about percent, so definitely we need to divide this by 100 in order to get this in levels. So when x changes by 1%, y changes by beta over 100 units, whatever y is measured in. When it might be the reverse. We may compute the logarithm of y and x in levels. And this is the case that you had in your home assignments. There was a logarithm of wage, and x is education in years. And look, the interpretation of this beta 1 is the reverse. A change in x by 1 unit is associated with 100 times beta 1% change in y. So back to that example in your home assignment. If education increases by 1 year, wage increases by beta 1 times 100%, not dollars, but percent. Why? Because we are talking about the variable which is in logarithms. And the third specification, as you may guess, is log-log specification. So this specification you will see in your last home assignment regarding the, so I will put something like a cost function to have a link with the microeconomics. So we have y in logarithms, we have x in logarithms, and in this case beta 1 means that if x changes by 1%, y changes by beta 1%. No need to multiply this by 100 or divide this by 100, it's simply beta 1%. And this is called the elasticity of y with respect to x. We spoke briefly about elasticity during our microeconomics course, and I'm pretty sure that you've heard about elasticity from other courses, maybe like introductory microeconomics or in macroeconomics. Probably you've heard about this, right? Have you heard about elasticity? Something like elasticity of demand, for example.
Yes, we heard about it. Absolute elastic term.
Yes, that's true. And this is exactly why if we want to estimate something like a demand curve, we estimate this in logs, because in this case, beta 1 has this natural interpretation of elasticity of demand. So suppose that y is quantity and x is price. Then beta 1 is going to represent the price elasticity of demand, so elasticity of demand with respect to the own price. The only problem is that you are not able to estimate this model in this way, but we will be talking about these problems in the second part of econometrics course. So please be careful. I specifically put this table into the slides for you to have a reference how interpretation of beta 1 changes if we change the variables from levels to logs. This is important because, as you see, the meaning of beta 1 is very different in all of these three models, and compared to the usual linear model, the interpretation is quite different. Now, if we fit all of these three models into the data, so I took these pictures from the book, we see that linear log regression, when test score is in levels and average income is the logarithm, we have this. And you see that now this function does not bend downwards because logarithm cannot decrease, right? So logarithm is increasing function. This is one kind of feature of this specification. And on the right hand side, we have on the vertical axis, we have not a test score, but we have a logarithm of a test score. And look what happens. If we put here a logarithm of a test score, which is the percentage change in the test score when district income changes, we have interesting observation that log linear regression doesn't change. It's a straight line. It's like a usual line. And it doesn't fit model. It doesn't fit the data. But log-log regression fits very nice. So therefore, we can treat that, or we can judge that either linear log regression or log-log regression is more appropriate to model this data. Well, when we estimate the parameters, we do this. And again, the estimation does not change. We change the variables. For example, if we want to estimate the first model, we need to first create a new variable, and this new variable is going to be the natural logarithm of average income, and then apply a familiar OLS in order to estimate this model. If you want to estimate the second model, we create a new variable, which is the logarithm of a test score, and we estimate the OLS of this logarithm on the level of average income. And finally, if you want to estimate the third model, we simply regress log test score on the log of average income. So all the previous technical methods are applied here, no difference. We simply play with the variables and we transform these variables into the more appropriate version, the appropriate to our goal and to our data. Well, if we look at the significance of all these coefficients, we see that all of them are statistically significant. And here is one additional thing that must be one issue that must be raised here. You cannot compare these models with the previous one, for example, with the cubic or quadratic regression. You cannot compare these models by R squared. This is a very important issue because R squared is built on the sum of squared residuals, of the regression sum of squared, etc. And if you transform your dependent variable into log, definitely the sum of squares changes. So therefore R squared for this second model and R squared for this first model, they are not comparable because they have different dependent variables. This is an important thing and you must remember this. So never compare log linear model and linear log model by R squared. Even if R squared is larger, this is nonsense. Yes, and as we see, linear log and log model fits data better, and we treat which model is better, not by R squared or not by F statistic or not by something else, but simply observing the data, the scatter plot, and looking at the line that fits this data. And moreover, when we want to choose from these models, there is another issue. Does this make sense to take test score in log? Does this make sense? Well, probably
really.
no. Probably no. We want to have test score in levels and income in percent because it makes sense to look at the percentage change in income rather than the percentage change in the test score. Therefore, the first model, if we are left with the first and third model, right? If we are left with linear log model and log model, and if we need to choose from them, so maybe the first model is better because it doesn't make sense to compute the percentage changes in test scores, but it makes sense to compute the percentage changes in average income. So therefore, we kind of believe that the first model also fits the data and we can perform some predictions or some analysis with the help of this. And yeah, basically I didn't put this into the slides, but I guess we still have some time. Let's see how we can do the same exercise. What happens to the test score when average income changes from 10 to 11, and what happens to the test score when average income changes from 40 to 41. So let's see. Well, if average income changes from 10 to 11, we simply put everything into the model and we compute what is going to be the test score. So test score hat equals well, what's that? 557, 83. Plus 36, 42 times the natural logarithm of 10. Right, so we take 10, we compute the natural logarithm, multiply by 36, 42, plus 557, 83. And we have this 641, 69. So now if the income is 11, we simply change this to 11 and we compute the natural logarithm of 11 times 3642 plus 55783, so it's 645,516. So the change, or the average change in the test score is 64516 minus 64169, so 347. So remember that when we used the second order polynomial, there was something like 290 something, right? So it's slightly larger estimate of this causal effect. Now, if average income changes from 40 to 41, we recalculate these two expressions. Put 40 here, we put 41 here, and in the case of first, we have 692 to 18, and in the second one we have 2, 7, 8, 3, 6, 9, 3, 0, 8. So the average change in the test score is gonna be 69218 no, sorry, 69308 minus 69218 to 18. So there is gonna be 0.9. So the same diminishing effect of average income change on the test score change. So for welfare income, for welfare districts, the test score tends to, the effect of the test score is going to be lower. Was there any question? And let's see also on this application what happens if we are using log-log specification, for example. So this is the test score, and that was the specification with log on the left hand side, on the right hand side, and level on the left hand side. But what if we are using this specification? There is gonna be log of a test score, and yeah, 6336. And here we have this 000554. So this, let's do the same exercise. Let's change the average income from 10 to 11. Now the only problem is that instead of test score, we have a log test score. How should we go from, so before calculation, the question is, how should we go from log to the test score itself? Any ideas? What must be here? What is the logarithm?
So logarithm. It is logarithm is the value of power.
Which power?
Power of exponential value.
Yes. If we are talking about the natural logarithm, then the following holds. If you take the value e, or exponent, and we put this to the power of, let's say, x, and this equals to, I don't know, let's say 4, then from here we can say that x equals to what? X equals to the natural logarithm of 4. And this is the inverse function. The exponential function is the inverse function of a logarithm. So if we have logarithm of something, and if we want to calculate this something, then we need to take the result and use this as a power to the exponent. That's correct. So we take e to the power of this. And this is one issue that we needed to raise here for you to understand how exactly you can calculate this prediction. So now if the average income changes, we are doing this calculation. We put 10 here inside the power, and there is gonna be what? There is gonna be 10 logarithm multiplied by 0.0554 plus 6,336. So here is the power, and now we take the exponent of this. Should we do this here? So exponent e the power of this. Yeah, so 571.78, very small. Okay, so let me check, maybe something is wrong. 10 logarithm times 0.00554 plus 6,336. And now this is the power of this. No, that's correct. Okay, and when the test score is 11, we take 11 here, and we calculate the result. 4 plus 6, it's 572.208. So on the average change in the test score is here. So it's 572.08 minus 571.78, and the result is 571.78. Oops, I forgot to put comma here. 208 minus 571.08. 78. Yeah, there must be like 0.3, which is strange, right? Because it definitely doesn't get the same results. So maybe something is wrong with these coefficients. Need to check it. Okay, but at least you get the idea. If there is a log specification, then you convert first in order to predict the level of this variable on the left hand side. You convert this into the following expression. You take exponent of this value, and then you plug x's accordingly, and you calculate what is going to be the change in the variable. Any questions regarding this? Basically, if you have a scatter plot and the scatter plot suggests you that there is some nonlinearity like this, you come up, you have a toolbox of different functions, and this toolbox was somehow developed in your mathematics courses in the school. Polynomials, log models, exponents, square root function, hyperbola 1 over x or 1 over x squared also might be good. And now you see that the first step in order to feed this nonlinearity to the data is to transform your variable appropriately, either to transform this into the polynomial or into the logarithm, or into, if you want, for example, to fit hyperbola, you need to calculate 1 over average income. And in this case, you will get the hyperbolic specification of the model. And you can test if this hyperbolic specification fits better than one of these two. And also something else. I mean, it is not restricted. You transform the regressor, you estimate coefficients on this regressor, and then you build the fitted line. And if this fitted line looks good, then you can use with this. But also don't forget about the economic interpretation, whether this specification, hyperbolic or something else, makes sense. Usually logarithms are good, and polynomials are also good, and hyperbolas are as well in some specific cases. The only one problem is that if x might take values of 0, then hyperbola is not appropriate, because if economically x takes values of 0, hyperbola is not possible, as well as logarithm, because logarithm of 0 does not exist.
Also, there was some detail about like, was the restriction or what, that the change is small, that the delta
What
x
do you
is
mean?
small. We had something on the slide that delta x should be small.
Yes. No. I mean, delta x is small is in order to give a correct interpretation of beta. So for small changes in average income, for example, look, let's look at this specification. What this 3642 mean? It means that if average income changes by 1%, test score on average changes by 0.3642. But we cannot say that if average income changes by 10%, test score will increase exactly by 364. Why? Because delta x now is not small. So delta x must be small, like 1% is okay. If we are talking about larger changes, the interpretation of this is going to be farther away. So for example, look, as I said, as we have calculated here, look, what is the average change in test score when income changes from 10 to 11? This is the 10% change, right? From 10 to 11, income increases by 10%. And the average change is exactly, we calculated exactly as 347. Look at this. If we want to interpret this coefficient with large changes in x, for example 10%, then the interpretation is going to be something like, if average income changes by 10%, which is large, the score changes by 364 points. But we see that we are missing this a lot, right? So the precision is not that large. Therefore, the correct interpretation must contain small changes in average income, like 1% or 2%. Then we will be closer to this effect. Okay.
But in the example we did a 10% change, right?
Yes, but we are not using this 10% change with the help of coefficient. We are using this directly. I plugged here 10, I plugged here 11, and I calculated the test score change directly. And directly, this calculation gave me this result, 347. Once again, look, let me demonstrate you. So for example, with the help of beta 1 estimate, I might have said the following. If average income changes by 1%, test score changes on average by 0. Well, we had this interpretation here. Linear log 1% change in x is associated with a change in y of 0.01 times beta 1. So, which means that I need to multiply this beta 1 by 0.01, and that is going to be 0.3642 points, right? But if I apply this logic proportionally to 10% change, I might set the following. I might have said that if average income changes by 10%, test score changes on average by how much? 362. And now compare this direct calculation, which is the correct one. This is the correct calculation, with this approximation. The approximation gives me larger estimate of this effect. You see? So this is where you need to apply these small changes in x. If you want to use beta in order to predict how much is going to be the change in test score when average income changes. If you are doing this directly, like I did here, doesn't matter. You can change x by 10%, by 20%, by 40%. If you calculate this directly, everything is okay. If you calculate this using the interpretation of beta, this is going to give you a large discrepancy between the exact change and your estimated change. Well, we need to move on. Think about this, and if it's still not clear, we can discuss this tomorrow on the exercise session. The second case of nonlinearity that we have started with was about different slopes of lines for different groups. And this is called an interaction between variables. So the question here is, what if the effect of one variable depends on the level of other variable? So for example, smaller classes have stronger effect on test scores in districts where many non-native students, and weaker effect in other districts. Well, it has some logic. If there are a lot of non-native English speakers, then probably reduction in a class size will get us larger effect on the test score compared to the districts where the number of non-native English speakers is small or even zero. In that case, this effect is going to be smaller. This is another case of nonlinearity. Nonlinearity because there is some heterogeneity, some difference in different groups, and the effect is also different. Well, basically, we want to model the situation when this derivative depends on x2, depends on the other variable. In the previous case, this derivative depends on x1. You have seen this when I took the derivative of a quadratic polynomial. The derivative depends on x1. In this case, we have two variables, and this derivative must depend on x2. You also might remember this practical example from microeconomics. In the microeconomics, we have calculated something like the marginal product of labor, marginal product of capital, and in some versions of those functions, marginal product of capital might depend on the level of labor. The more labor you have, the more is the marginal product of capital. Something like this. The same idea here. And we call a specific tool in order to model this an interaction term. So here is an example how the interaction term looks like. We take two binary regressors. We will start with the simplest case of two binary variables. So here is D1, here is D2. And also we include this. We include the product of two variables. And this product is called an interaction term. You might remember this from our exercise sessions when we used, for example, the regression of a baby birth weight on smoking and on alcohol consumption. So we had two binary variables. But we didn't have this. We didn't have this interaction. And this interaction has a very interesting interpretation. Because in that case, in the case of that birth weight regression, we might see also if smoking for a lady who consumes alcohol has a different effect on the birth weight compared to a lady who smokes but does not drink alcohol. So, depending on the drinking or not drinking alcohol, probably smoking gets more negative effect, gives larger negative effect on the birth weight. Let's say like this. Look, the interpretation is very simple. If you plug D2 0 here and here, so what is going to be the effect of D1 on Y? This effect is beta 1. Everything is simple. But if D2 is 1, then effect of D1 is beta 1 plus beta 3. So this effect changes. Look, because if D1 is 1 and you change, if D2 is 1 and you change D1 from 0 to 1, then the effect is going to be beta 1 plus beta 3. This is the way how we model this nonlinearity and the effect of one variable, which depends on the level of the other variable. So let's see this on our example. Let's define two variables, two binary variables, which applied on our test scores example. One binary variable is this high STR, which is 0 if student to teacher ratio is less than 20, and 1 if the student to teacher ratio is greater or equal to 20, which means that this is a binary variable for districts with large classes. And another binary variable, high EL, which is 0 if there is a low level of English learners, and 1 if there is a large level of English learners. Again, 1 if there are a lot of migrants and 0 otherwise. And now we estimate the following multiple regression model. We plug one binary variable, the other binary variable, and their interaction term. Let's try to interpret these coefficients. Well, those of you who are attentive enough can see that this is not significant, this is not significant, but still. Let's try to interpret the coefficients first. If they were significant, what will be the interpretation? Look, for districts with small level of English learners, so for districts with a small level of migrants, the effect of a large class is minus 191. So basically, if you take districts where the percentage of migrants is not large, the difference between test scores in large classes and small classes is 191. For districts with the higher fraction of English learners, high L is 1, the change from large class to small class changes the test score by 5.4. So this is a nonlinear effect. The effect of a class size depends on the level of the other variable. This effect depends on the percentage of English learner students. But the problem is that interaction term is not statistically significant, and in principle, we cannot claim that there is such nonlinearity and there is such heterogeneity. So this term is statistically not significant, and we reject the hypothesis of such nonlinearity. But as I said, if this coefficient were statistically significant, then this claim will be valid. Is that clear how this interaction term works?
Yes, and also we should apply it by our logical by the logic if it is applicable in this situation.
Well, yes, in many practical in many research in many papers that are published when this econometrics is applied, researchers want to see if there is if there is a different effect of one variable on the other for different groups of people. For example, for women and men, or for people with a different level of education. This is something resembling ANOVA, but now we are not simply comparing means, we are comparing the whole regression lines. We are comparing the regression line for example, males and the regression line for females. Or we are comparing the regression line for districts with the large test, with a large percentage of English learners and small percentage of English learners. And of course, yes, you must have some rationale before building this regression model. You must at least suggest that maybe there is some heterogeneous effects between different groups of objects, between different groups of people, firms, stocks on the market, industries, countries, whatever. And this is a very powerful tool to show that there is such heterogeneity. So for example, yesterday we've been discussing with one of my students a paper, and in that paper authors published the following result. So they compared how different, let's say, methods of management in the firm affect the firm performance, like profitability of a firm, for example. And they use these interaction terms, and the second variable for this interaction term was the development of economic institutions in the country. And the idea was like, if the economic institutions are well developed and everything is predictable in the country, then the managerial methods that are mostly work well planned and stick to some plan and stick to some goal, they work better. Otherwise, managerial methods that are more, let's say, adaptable and flexible work better in those countries where the economic institutes are less developed. And this is exactly about interaction. So they estimated the regressions with this interaction term. They show that, well, one method works and has the higher performance in countries with better developed institutions, and the other method works better in countries with less developed institutions. And this is the same idea. Yes. So whenever you want to show that your objects are not homogeneous, your objects are different, and they might have different effects, you apply this interaction term. You may see this interaction term in many different regressions, in many different models. So basically everything that we are talking about today is the most interesting cases when we apply all these models. You will rarely see simple or multiple regression, and that's it. You will usually see something like these interaction terms, polynomials, logs, and many other things. So let's speed up a bit. There are two additional cases about the interaction term that are very similar. What happens if we have one continuous variable and one binary variable? In this case, the logic is the same. Binary variable changes, switches the groups, and the continuous variable is simply computing the effect of showing this variable, and shows the effect of this variable on the outcome variable. So there are three possibilities how we can apply the binary variable. So one possibility is this. It is familiar to us when continuous variable is separately, binary variable is separately, and in this case we will get the same slope, the same estimate of the causal effect, but different intercepts. And usually we don't care about intercepts. Another version is here, when we plug continuous variable, when we plug binary variable, and also we plug their interaction. In this case, we will have the situation when both intercept and slope differ for different groups of objects represented by this binary variable. And the third, which is redundant, and you will almost not see this model, is when we plug continuous variable and interaction term, and we don't use the binary variable separately. And here is an illustration what happens. In the first case, both lines are parallel and only slope changes, and the slope differs by beta 2, by this coefficient. In the case of interaction term, we have two lines, and these two lines differ by intercept beta 2 and also by the slope. The slope for the first line, where d is 0, we will get this formula beta 0 plus beta 1x, and for the second line we will get this formula. So intercept is beta 0 plus beta 2, and the slope is beta 1 plus beta 3. So you see that for one group the effect is stronger, and for the other group the effect is weaker. And finally here, when we don't include the binary variable separately, they start from the same point, but they have different slopes. And this different slope is exactly what we are looking for. We are looking for the different effects of x dependent on the binary variable. And here, if we continue the example about the student-to-teacher ratio and test scores, now instead of using this high str and low str binary variable, we use str as it is, right? So we use this as a continuous variable, plug it here, and we have the following estimated model. Interaction term is not significant as before, but again, let's abstract from this and let's try to understand what happens. So when this binary variable is 0, the regression line is this one. If the binary variable is 1, the regression line is different. And here is the catch. Here's what we are looking for. If a district has a small fraction of English learning students, then increase in reduction in the class size affects test score slightly, right? So 0.97 is a small effect. While for the districts with a large percentage of English learners, the effect is stronger, 2.25. This is the example, and usually you will see this example in different types of research. You can show that for two different groups of objects that you observe, the effect is different. But on the other hand, the coefficient on this interaction term is not statistically significant, so you cannot claim that this effect is different. And the last case, I will very briefly go through this. If there is an interaction between two continuous variables, the idea is the same, but now instead of binary variable, you have two continuous variables. The interaction term is the multiplication of them. And now we can apply calculus. We can take the derivative in order to get the effect of x1 that depends on x2. Here is an effect. We take derivative of y with respect to x1. We get this, and you see that this effect changes if x2 changes. For example, if beta 3 is negative, the effect diminishes. If beta 3 is positive, then effect becomes stronger when x2 increases. So this effect of x1 depends on x2. Something similar to the quadratic specification, but now we see that it doesn't depend on itself, but it depends on something else. Here is the estimated model for our example when we regress on two continuous variables, and the coefficient is also not statistically significant, but I wanted to show you the application. For example, if you take the median district and the effect is going to be minus 111. So the effect when we reduce the test score, when we reduce the class size, the test score will be improving by 111. If you take a district with the 75th percentile, which is 23.02, this value, the effect is going to be slightly smaller, which basically contradicts the previous finding, right? When we used the binary variable instead of ELPCT. But again, this coefficient is not statistically significant, so we cannot claim, finally, we cannot claim that the class size has different effect on test score in districts with a different level of English learners. Yeah. So this is all about nonlinear functions. So as you see, we can do a lot of meaningful economic analysis with the help of these functions. We can adjust the regression function to the more sophisticated data and answer more sophisticated questions than before. And we can make these nonlinear causal effects dependent on the levels of other variables, which makes our analysis very flexible. And with this, we finish the first part of econometrics, because, as I said, so now we understand all these possible specifications of models that might be estimated with the help of multiple regression, with the help of OLS. So congratulations. Now we can do a lot of interesting things in economic research. And in order to see how this might be applied on our example, you need to read this paragraph 8.4 in Stock-Watson. As the last week, you will get a quiz on this lecture and also on the material of this paragraph. It will be available till Saturday evening, Saturday midnight.